Or no, something else.
I was looking at the quiz.
Oh. Why is that?
Because when you get to the other side of the circle, you're gonna have a 0.6 radius and Mars 1.5.
Oh yeah, yeah, yep. And quiz 2. Yeah, could it keep moving? I mean, yeah. Yeah, normally everything's not like two-dimensional, like all slamming into each other. It's like out of plane. And that's fine.
Yeah, I feel the other way around. Typically, you usually use the system like an engine block where it would all be on the same plane.
But even that, you'd have like think of a piston crank, you have like two connectors that are out of plane with the actual thing moving, like a camshaft. Same thing here. Like we just simplify it down to like something moving in a circle. But yeah, that's a good point thinking about. Yeah. But yeah, if you want to think about like you push on it and then it like everything breaks. It's always fun to watch things fail. No? Watch it work. Yeah. It is satisfying to see things like actually work the way they're supposed to work. But when something like big failure, sometimes that's kind of cool too. And then understanding like how to fix it, I guess would be the best part. Yeah, hopefully not expensive. This was just a quick scalable vector graphic, so that's not expensive. Okay, welcome back. Another day, another week done. Like, I mean, I know like most of you still have another class coming up after this, but it is Friday afternoon. We're almost there. It's almost the weekend. Not yet? Long afternoon coming up? No exams. Are there exams today? All right. Yeah, no. Oh, and a project. Oh my God. Okay. But so we pulled this up. So there's a discussion at the beginning about like the kinematics of this motion. But I pulled it up. Thought it would be good to look at it anyway. Last class we talked about what were some ways to demonstrate learning in Module 2. Based on conversations that I had with a few different people, this kind of felt like it was doable. Of a little combination of that first problem in homework 1 where we were looking at a flywheel that we know how fast it's rotating, what force do we need, and then add a little bit of like kinematics. Like now we have this connecting rod between a piston and that thing. So what F do I need to create rotational motion? And the weird thing here is like when I apply a force, it's going right through the center of that flywheel. So as a system, F creates no torque. But because it has that connecting rod is creating the torque. So there's equal opposite forces, kind of, it's turtles all the way down. Turtles here, turtles there. Yeah.
Are we supposed to consider like the reaction forces that like for the active being pushed? Like, do we consider those forces?
Yeah. So
or, like,
this.
The ground, I don't know. I feel like I was like doing it in the time of 2 minutes ago, so I thought that was kind of doing too much.
The main thing is like we do have like a lot of equal opposite kind of reaction forces. But because like the only thing that's creating torque around here is that reaction force on that pin. It's the only thing that can cause it to spin. So we do need to think about like what is that force if we want to know what is angular acceleration. But then there's also like the flywheel itself is not moving left or right, so it's got to have some kind of stabilizing stationary forces to keep it there. Yeah. It should all kind of work out. It's not over constrained or under constrained, like it's just the right amount of constrained. Okay, so then the other thing that's coming up is our Module 2 project. So that's what I wanted to take a look at today and just play around, break some Python code, try to fix it. Just like, main thing is you're sort of like experimenting with something that's giving us more results. So our project 2, if I come down here to module 2 and project 2, and I loaded up like the NanoHub Jupyter like interface so that I can click on and start editing these things. If we do from the beginning, like if you go to the syllabus, you can get straight to that NanoHub server from here. And then usually it'll say like, hey, you need to like, do you want to log in? And then you can say, yes, I would like to log in. I'm Ryan Cooper. Welcome to Engineering Dynamics. And then it brings you to this page where we can come down to project 2. And I'll just give like a quick tour of what this is doing, and then we can like dive into like what can we change and how do we work on this. So this is like a Python. It's a pretty simple. Is it simple? No, it is a very specific, not necessarily simple, but a very specific set of Python code so that it will solve any 4-bar linkage system that we want. But sometimes we'll break things and that's okay, other times, because there are certain 4-bar linkages that can't move as much as other 4-bar linkages. So first, I'm just importing stuff that I want to use. Then I'm going to define my system with 25 centimeter, 100 centimeter, and 100 centimeter links. So one of them is, and that's similar to like the homework that we had, 25, 1 and 1, or 0.25, 1 and 1. But then my dx is going to be 0.95 and dy is 0. And that's what these variables, that's what it looks like in Python language. Like these are the variables, those are my link dimensions. And this f bar, this is a fancy way of setting up our constraint equations so that now Python can solve it for us. So rather than going through like how we were setting up systems of equations, I can say, hey Python, here's a system of equations, tell me when it's 0 and tell me what input I need to create a 0 out of it. And once I can do that once, I can do it 100 or 2,000, as many times as I want. I can solve for as many systems as I feel like. I'm gonna go like start angle 1 at 0 and go all the way to 360. Sorry, and then question.
How did you go to that Jupyter part from syllabus?
Oh, from the syllabus?
Yeah.
All right, let's do that. So if you're on the syllabus, when you went down here, like over on this left-hand side project.
Yeah, I'm on model 2.
Okay, that works. Then you can say, click on the little rocket, and then launch into Jupyter Hub, and that'll bring you to. It brings you back to the home page of saying like this is everything in our course. But that'll get you there. So because I'm trying to change theta 1 to go from 0 to 2 pi, like 0 to 360, I'm going to set that A1 0 to 2 pi with that linspace. And then A2 and A3, you don't have to worry about it. If you're like staring at it, like, why is this? It's called initializing the arrays. Like, I know what shape I want them to be, I just don't know what they are yet. So I'm just gonna say create a vector, and then I'll plug in values as I go. And that's what this for loop does for me. It's like that F bar, I'm gonna go from 0 to 360 and solve for all of the angles for every theta 1 value. Once I have that, I have like all that kinematic information that we were trying to figure out in the homework of like, if theta 1 is this, then what is theta 2, what is theta 3, and we were looking at coordinates of where those things are. All of this is just kind of plopped out in a couple of lines of Python code. So this is really like the power of using a little bit of engineering and a little bit of like programming kind of skills. And I know where all the link locations are. If I know the angles, then I know like what they look like. So I can plot, I can find the X locations, the Y locations, and start looking at the path of every one of my arms. So here, blue circle is A, like that hinge point at A. This red line is looking at the rocker motion. And then what is that green like egg? What is that thing showing? Point B.
Yeah, first bin. Well, technically second, but first corner.
First corner. And right now I'm showing like theta 1 is something like, I don't know, 80 degrees, but I could change this. We could look at when theta 1 is 0 degrees. The path doesn't change because it's just showing you all the locations where things end up. But that green, what is that green one doing? Why does it look so weird? Yeah. No. 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 It was more of a, sorry, I misread. Someone went like this, and I thought it was like a hand up. What is that green point?
Isn't that just like the reaction of the second bar because A has to be going around, so the midpoint of A is going to have to do that?
Yeah, yeah. So because we have like a combination of something moving in a circle, something moving in an arc, it's always connecting that circle to this arc with one link location. Yeah. What is that helpful? Is this ever helpful? Like, why would you want to do something like that? So there, at least for like you can get all sorts of cool motion out of it. In here, I'm gonna run through and just hope, I'm gonna assume that it's all gonna work. Let's see. And so far so good. Takes a second to load up animation, but you can create like any kind of path, not any kind of path, but lots of different paths from that midpoint. So sometimes that's used for like complicated motion, but you only want to use one actuator. Like you only want to use one motor, but you don't want it to move in a circle and you don't want it to move like in a straight line. So like if you were trying to draw a heart, it's like I know Valentine's isn't coming up super soon. Maybe I should draw like a skull for like, yeah. But yeah, we can get like all sorts of these different kinds of motions. Yeah, it flips over pretty fast, but it still draws the heart. So that can't, so sometimes when you think about like what is the design of a 4-bar linkage and what do I care about, sometimes all we're trying to do is take rotating motion and turn it into back forth motion. Like pumping is a great example. Like I don't want to stand here and pump oil all day, so I'll set up a motor. Motor's gonna turn and it's gonna run a pump for me. Other times there's stuff like positioning. Like I want to take an object, pick it up here, move it around, avoid something, drop it somewhere else. So 4-bar linkages could do that for us. Okay, so then coming down, the default drive rate is like around about a little more than 1 rotation per second, like 10 radians per second. So then I can solve that same system of equations that we did in homework 2 to figure out how fast is everything moving given like an input drive rate. And now not only do I have it for like one specific point in time, but I could solve for the entire range of motion. That here, link 1 is always moving in a circle, 1.2 rotations per second. Yeah. Meanwhile, link 2 is kind of bouncing back and forth. Link 3 is oscillating back and forth, all at a smaller amount, like up to 1/5 of what my input drive is, to the 10/2. So your goal, so that's roughly, that's the crash course to get through the notebook is hold shift and enter, 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 and then you do get results. You get numbers, you get graphs, off to a good start. So your goal is pick your own 4-bar linkage, like what kind of design you want to do. Some people have like general goals, like I want to see how fast I can get, like we were just looking at the heart kind of flipping around. Like maybe I want to see how fast I can fling something. Like someone was trying to like imagine, what if I had a 4-bar linkage catapult? And I could design link 1, 2, and 3 such that link 2 has the largest theta2 dot that I can possibly get out of the system. That's one thing. You could do something like that, or we could think about like what are some existing 4-bar linkages, like a windshield wiper. We know, Maya. We know. There we go. So like windshield wiper is a 4-bar linkage with like one extra set of it's like 2 4-bar linkages connected to each other in series, and that's how your windshield wipers work. It's all like under the hood of your car. Or the ACL, PCL joint, like your anterior and posterior cruciate ligaments. We already know that. And this one, I don't love this animation because it kind of looks like your ACL and PCL are stretching, but it does. But like roughly, if you know the length of your ACL and PCL and where they're connected to femur and what's that bottom tibia? Tibia, is that right? So if you know where they're connected and how long they are, then you could have like a 4-bar linkage of what the knee looks like. Because this connecting the joint that's in here is not around, it's not a ball and cup. It's actually like it looks the same, similar to that green shape that we just saw. It's the midpoint of that A and B connection. So if you create a artificial knee that is just a round joint, then you'll throw off someone's gait because it's not moving the way that they want. But if you model it after a 4-bar linkage, then now the knee is bending the way that the person is expecting it to bend. And every person has a different shape of their knee, of that joint connection. So there's all sorts of stuff that we can do here. And then the Watt linkage. Do you know what this is? Have you heard of this? The Watt linkage? Where would you see this? In a light bulb? Light bulbs are usually like all static. Would you need suspension in a light bulb? I don't know. Depends on the light bulb, I guess. I don't want to say no because I've not come across BMX. Usually not bikes. So this one, but it is like it is a suspension. So bikes do use like a 4-bar linkage suspension in the rear, but not the Watt linkage is a little different.
Independent rear suspension.
Sorry?
Independent rear suspension.
Yeah, usually for rear suspension, so that I can hook a wheel up here and I can hook a wheel up there, and as the car is bouncing down the road, the wheels are not like changing their angles. So the car is bouncing, meanwhile my wheels are still flat on the road. This would be like if you're interested in kind of like car suspension mechanics and you want to look at these kind of kinematics, this is an example of like, I can't do a full 360 rotation of that first link because it's going to snap my suspension. So there's going to be some kinematic limit to what angles I can put in there. But all sorts of stuff. Or if you find your own examples of like what a 4-bar linkage could be used for, then you could try modeling any of those. Yeah. But that's the goal, is connecting 4-bar linkages to something. Like what is a project that would make sense to you? And then like once we have a design goal, now the question is like, what makes your 4-bar linkage like usable or not usable? Like, is there still future work that needs to be done? Something else needs to happen, or is it good? Everything's great. But we have the tools, now we can start doing some real engineering design. At least 4-bar linkage engineering design. Cool. I know there are questions, but you might not have them like formulated yet. Does anyone want to start with an unformulated question?
Does a 4-bar linkage apply to a bar?
A 4-bar usually, so with every 4-bar linkage, there's always 3 moving parts. So if we're looking at this Watt linkage as it pops up, we have 3 moving bars and then the fourth link is like that last connection between these two X points, this X up here and that X down there. So that's like the fourth bar. So sometimes people call it a 3-bar linkage. 4-bar is like the, I don't know which one's more accurate, but 4-bar. Usually I hear 4-bar more so than 3-bar. If we didn't have like those 2 points disconnected, then it would just be a triangle, and then triangles are boring. That's for like reinforcing bridges and stuff. We want to have like moving parts and transformers. Yeah.
What kind of rear suspension is this? It reminds me of like the way it's set up was described as like independent. It looks like a dirt bike.
Like a dirt bike frame? Usually dirt bike frame.
You have a one shock in the back and there's one on that goes up and down.
4-bar. Like dirt bikes and like mountain bikes, they all have similar kind of setup. Oh my god.
This video, I'm going to focus on what's going on back end. Yeah, we have the lower stars to connect my brain. That's like changing. Is it before the actual finish? First part.
So dirt bike, mountain bike, similar idea. But your like main kind of moving parts are like this one. So if I think of it as like O, A, B, and C, and then there's like the connecting thing. And then there's extra like rigid bodies connected to it so that I can control the motion with pistons and springs. But definitely like that rear suspension, use a 4-bar linkage so that as it's rotating, you're not changing the wheel length, the wheelbase. And that's why you use like a 4-bar in a mountain bike or a dirt bike. Because otherwise, if all you did was let it like rotate up, then when you hit the ground, your wheelbase shrinks, and now it's less controllable. So, which is the worst time to have less control is whenever you're slamming into the ground. So they try to eliminate some of that by like, or even sometimes like increase the wheelbase as you hit the ground. Yeah. Good eye though. Yeah, definitely 4-bar is a great like suspension mechanism. And the main thing there is like you only need one actuator. Like it's not, you're not controlling like lots of degrees of freedom. 4-bar still has just a single degree of freedom for motion. Nice. So many tabs open now. Oh, I didn't even get to the right one. Oh, project. Okay. Other question? No. Let me check in, see what people are looking at. Not down. What? Yeah. So when you say file
You can change it to whatever you want, and it doesn't work. That's why I changed it. And I don't know if it works. I don't know what happened.
Yeah, no. Yeah. But that's fine. You should be able to change whatever you want. Like main design changes are just those link links and the location of where they're going. Okay, so we have that. You shouldn't be. Okay, yeah. Unless you like, there's other further analysis that you keep doing, like if you're doing it, you're like, how do I see something? Yeah. Then we can work on it together. Okay. But to start, like just first, very 45, like 5. Yeah.
Like, how do I know what like I know I'm having like a deal like which one? Or like
Yeah, because ACL, PCL, really wants certain regulations. And really, it really is kind of like beta 2 main range rather than beta 1, but they're all in there. If you send it to them,
I tried to do something and then it gives you like remember like we can just change numbers around.
yeah, to start, like just play around and do whatever you want. And then as you get a feel for it, it relies on either a certain design goal or like an ACL, PCL, something you want to try.
Yeah.
Okay, whoa, I was wrong. That's not how you change what you
So like
change.
just
Did you change the
Yeah, like main thing, like
oh, that makes a lot of
yeah.
like when I was in
Does it change it every time you run it?
Okay.
11.2 centimeters. That was the number. My MOD.
No, it's just
Yeah, but it'll get you like the ballpark.
no. I just changed it to 0. They're both to 0. Yeah, can you buy both 0? Oh yeah, I'll figure it out. There might be. That shouldn't be an issue. You change the FUI.
So this is a main one. So if 0 to 16. Like ACL.
Oh, there you go. I got a circle. I just got green. I think that's the one. 3 bars, 4 minutes. I don't know. I think maybe Saturday night. Michael Fish.
Oh, yeah, I'm a semester.
Oh, I think that.
Like you can, like if you just want to play around with like different geometries, then just geometry.
Oh, Sunday, sorry.
Really fast.
We go with the
Yeah, so if you change this from like 2.5
like the Wi-Fi
then you can run it.
Okay, if I go back to 0.25, 1, 1, just keep running them. Oh yeah, see, they started there. This is what we started with. They can't really start with. Maybe they have to back it.
So we made that first like smaller, so we don't angle smaller.
There you go. That's back where we started. Okay. One has to be short.
Smaller angle. You can't do it tonight.
Not the worst in the world. If I change this,
Why don't you tell me what you want to do? And I'll say like, yeah, go for it. That one, yeah, because you're like the crank of the bike is the crank of it, and then your shin connector, like the lever ends up being the rocker. Yeah, perfect. Yeah, otherwise you end up but then there, like, you can get super into that because you could build your own like seat positioning parameters, like move the seat back 5 millimeters, that would be like quad like distance. it depends on the bite, but I think it's usually but yeah, it's up to you.
Remember all the stuff you were doing?
You could do, you know, yeah,
So what are the DY and DS?
that is like there are 2 points that don't move, and one of them is always at 0, 0. The other one is at time.
I think that's what I'm, and then I think it's
Nice. Yeah. Yeah. All right. Cool. So now we're getting to the fun stuff. Stuff breaking. That's what we want to see. Yeah. Do you know what's breaking?
my best guess was rotate fully
Yeah. Okay.
because when we have it, consistent, that will pop up. But
Yep.
we can just hold it fully.
Yeah. No, that's a great. And one way you can, anytime you see like, if those curves are not smooth, then there's something weird. Because really you're just connecting 2 points on 2 circles. So there's a big sharp disconnect. Something weird.
Well, that's it, right?
If there's a yellow line, that means something is bad. Because point C is supposed to be fixed to the ground. It means that there's like yanking it around. Yeah. Yeah, same thing. It's just it's not like it's not bad. Yeah. But there you're like, okay, here's my linkage design. Yeah, what how is this supposed to work? Yeah.
That's what I like. And this time.
Oh, just yeah, and the main thing is that it just if you submit nothing, then it'll give you a 0. But if you submit a note that says it'll be here Monday, then we know that you have a plan. Yeah. Are we out of time?
Oh.
So we got so we got time. All right. All right. So we started seeing. I started seeing like some broken stuff. So let me leave L1 as 25 centimeters. L2, I'm gonna make it 10 centimeters, really small, like half the size of L1. And then L3, I'm gonna leave as a full 1 meter, full 100 centimeters. And let's see what happens. And again, if you want to like run through this real quick, you can hold Shift and hit Enter, and it'll keep running stuff. All right, here's our first like big thing. When I try to run the solutions, it's telling me like, you have runtime warnings. Are you sure you know what you're doing? And if it's pink like this, then it just means it's warning you that things aren't going the way you thought they were going. But it still gave you an answer. So it's like, all right, I'm going to ignore everything you said. Just keep going. Because I did get answers, but my answers look very odd. Because now I have like angles were one thing, and then they changed by 800 radians, and then they were something else. That's not an ideal system. I mean, it depends. Like if you want a catapult that launches something at 800 radians per second, so times 1 meter, now it's 800 meters per second, and maybe that's what we want. But let's keep going ahead. Shift Enter. Let's look at the paths and see if we can find anything else. Now I start to see like what's wrong with this problem. And like the main, at least for me, the first thing that I see when I look at this, and I've broken it countless times now, So when I see a yellow line that's plotting the location of hinge C, which is supposed to be a fixed point, it's always supposed to be in the same location. If it's moving, then there's something wrong. I'm breaking in order to get a solution, I had to break my kinematic constraints. That's what those warnings were trying to tell me. It's like, we gave you an answer, but really you're never gonna get a good answer from us. So here's the best we could do. So it gave me locations, and it has like a weird like Eye of Sauron sort of thing. I don't know. Like that red in the middle too. So there's a couple of ways that we could fix this. Let's look at a different location. Like maybe I think I do know what I'm saying. Maybe I think this system should work. It's just maybe it can't work for every angle. So maybe I want to reduce the range of motion. Maybe just from like what would work. Like I can't go 0 to 2 pi. Maybe I could go np dot pi over 2. Or no, it still doesn't like that. Oh yeah, it still doesn't like this. Oh, so maybe I want to go pi over 2 to something bigger. And now I'm like changing. I only went like 10% of 90 degrees, so I only went 9 degrees, but but it's not breaking anymore. So that's like one thing that I could do is change how big of A1 I want to actually solve for. The other thing is like change the actual link lengths. Like I probably don't need a 1 meter thing connected to that 10 centimeter thing. And yeah, or I could come back up here and say, all right, well maybe this doesn't need to be a full 1 meter. Maybe I could just get away with like 0.2 meters, and then this one 0.4, so 0.3. Maybe put that 0.3, 0.2 plus 0.1, maybe 0.1. Oh, didn't like that one. Yeah, and there's still something breaking because that link 1 is longer than link 2 and 3. So I gotta reduce link 1 or increase link 3. Something's gotta change, right? Make it 20 and 21. Ooh. So it's still moving like a little bit. So there's something that I need to like play around with there. But yeah, the main thing like for today was just sort of play around, try to break it, notice that it is broken, and then iterate towards better solution for the project. And then we can start making some design choices. Progress. I know we're out of time, so we'll call it a day. If you do have questions, stop in, or just have a great weekend, and then we'll see you Monday.